Welcome to Part 9 of Unit 2 of Quick Precalc Review. In Unit 2 we've been thinking about the topics that you see here in the context of compound interest problems, and especially focused on thinking about the compound interest formula in lots of different ways. Recently, starting with Part 7 of Unit 2, we talked about the special number e, and we also introduced the idea of a limit to ultimately define e in terms of limits. Part 7 was a very intuitive introduction. In Part 8 we got a little bit more rigorous. Here in Part 9 we'll get even a little bit more rigorous, though still not completely rigorous. We'll make use of Mathematica and these commands to geometrically visualize the limit of this expression in this video. The fact that 1 plus r over n to the n power approaches e to the r power as n goes to infinity. Again, for fixed r, 1 plus r over n to the n power goes to or approaches e to the r as n goes to infinity. Part 9 we'll get into talking about exponential alternative representations of exponential functions, including use of the number e in those representations, and we'll talk ultimately about logarithmic functions as we close out Unit 2 in the videos to come. Alright, let's start by going down and looking at this right here. We were thinking about so far recently the values of 1 plus r over n to the n power as n got larger and larger. That's also the value of what I call b, the actual annual growth factor, and it was related to the APY, the annual percentage yield, which represents the actual percent of growth each year. We saw that this expression gets closer and closer to e to the r for fixed r as n gets larger and larger. A little bit more precisely, this expression gets closer and closer, in fact as close as we like, to e to the r as n gets larger and larger without bound. We can make the distance between this expression and e to the r as small as we want, as long as n is sufficiently large. Here's notation we used for it. It's very important that you write this notation in the way you see it here, making sure you put the limit sign in there. It's also important that you verbalize it in the following way. You say the limit as n goes to infinity of the expression 1 plus r over n to the n power equals e to the r. You can also use approaches instead of goes to. You could say the limit as n approaches infinity. Doesn't mean infinity is a number. N is just growing larger and larger without bound. The limit as n approaches infinity of 1 plus r over n to the n power equals e to the r. Of course, if r is equal to 1, 100% interest, that also means the limit as n goes to infinity of 1 plus 1 over n to the n power equals the number e. In fact, this is sometimes taken to be the definition of the number e, not something you have to prove, but a definition. Though you do have to prove before that definition that this expression has a limit to begin with. It is also common to write this in another way, with this phrase, so to speak, 1 plus r over n to the n arrow e to the r as n arrow infinity. You don't say arrow though, you say 1 plus r over n to the n power goes to, or approaches, e to the r as n goes to infinity. That's an alternative way to write the exact same equation as this thing. I emphasize once again, this does not mean the expression 1 plus r over n to the n power ever equals its limiting value. And in fact, you can say with this example, it never equals it. For a fixed r, no matter what n is, this will never equal e to the r, no matter how big n is. But it does have e to the r as its limiting value. There are some examples of things that do equal their limiting value, so you should not rule that out, but in general you should not assume the expression you're taking the limit of ever equals its limiting value. Alright, let's look at the code we looked at last time as well. Here is the expression for b. In fact, I probably should have called this b of n. This is defining a function in Mathematica. It's not equal to e, so I probably shouldn't use the letter e there. It represents b, it represents the annual growth factor, 1 plus r over n to the n power. As a function, I can now plug things into the function like 1,000. It's a humongous fraction there. There's the fraction bar, by the way. Let's get a numerical estimate for that. I can do it this way, to estimate it, say, to 20 decimal places, like that. I can have Mathematica take the limit of it using the function limit. In this way, the limit is e. That is a special e there. It's not a regular looking e. It's not like I typed it. You see the extra line in there. That's representing the number e. Capital E represents the number e as well. And I can Look at this. It's a small number on the order of 10 to the negative 6 power. What is this thing representing? That's the absolute value, ABS, of this difference, b of a million minus the number e. I said in the last video, I'm going to re-emphasize now, this is very important, the absolute value of the difference of two numbers represents the distance between them. I'll say that again, write it down. The absolute value of the difference of two numbers, say a and b, the absolute value of a minus b or b minus a equals the distance between them. Let's elaborate on what that means up here. Okay? This means, let's write it out with mathematical notation. The absolute value of 1 plus, talking about this particular limit here, r over n to the n power minus e to the r power, that absolute value, that distance, can be made as small as we like by taking n sufficiently large. Okay, the absolute value of the difference of those two expressions represents the distance between them. If this limit is true, that distance should go to 0. We can illustrate that with manipulate. We'll go back down here, put this inside of manipulate, change the million to, say, a little n. N is going to be the animation parameter. It's a discrete animation parameter. I'll start it out at 1 and go up to, say, 100,000 in increments of 1. Not that you couldn't calculate it for non-integer values, but just to emphasize, we're thinking of n as being an integer. And I can make that animation and see the value going towards 0. That's the distance between b of n for these different values of n and the number e. Okay, and I can make that as small as I want. Like, that's going monotonically towards 0. It's decreasing towards 0. There are some examples where that doesn't happen, but if the limit is going to be true, the limit as n goes to infinity, this distance does still have to go to 0, though it might go to 0 in an up and down way. There are examples like that. Alright, for the rest of the video, I want to focus on visualizing this and looking at some Mathematica code. Here I've got Mathematica code that's going to give us these two graphs. I'm going to show you the Mathematica code in a little bit more depth after I think about the graphs. What are these graphs? Well, I have labeled them in the way you should think of them. The blue curve on the left is the graph of y equals e to the xy axes here. The red dot on that curve is the dot whose coordinates are r and e to the r. R is an animation parameter. Here it's fixed at 0, but I can change r and the red dot moves. You see the red line on the right also moving as I change r. That's a horizontal line. It's the graph of y equals e to the r as a constant function of n. I'm labeling the axes over here n and y. That's a constant function of n, or x if you prefer. All right. For fixed r, that the graph that is a horizontal line. The black dot is the value of 1 plus r over n to the n power when n is 1. The b here is also an animation parameter that tells you the largest value of n you're going to make for the dots over here. I can increase b and increase the number of dots. What are we seeing here? We're seeing that no matter what r is, okay, the value of e to the r is the second coordinate of this red dot, which is also the second coordinate of all the points on this horizontal line. You can take b to be big enough, which effectively means you're taking n to be big enough to get as close as you like to the red line, no matter what r is. Different r's are going to give you different rates of approach, but you always will approach that horizontal red line when n is sufficiently large. Why does that work? Okay, I'm going to quickly go through the Mathematica code a little bit here to convince you, if you've watched previous videos, that you could enter this stuff on your own. You could program this. Again, manipulate is the animation command. The grid is inside the manipulate right here. And after that grid with the comma, you've got these animation parameters. And here the label style just makes the R and the big B big. Inside the grid, what does grid do? Well, first of all, the basic structure of what I'm using for the grid is like this. Actually, I typed it already up here. Like this. This structure produces a grid, a matrix. It's going to be a 1 by 2 matrix by the way I've done the curvy braces inside here. The thing in front of the comma is in the left side of the matrix, and the thing on the right to the right of the comma is on the right side of the matrix. That's what this is. It's a 1 by 2 matrix of graphs. The one on the left over here and the one on the right. So the one on the left comes from this. Show again combines graphic objects. What am I combining there? I'm graphing e to the x in blue. You can see that's in blue down there. I'm graphing the dot, the red dot, e to the r, or r comma e to the r with ListPlot. R is an animation parameter. Here's the red dot for a fixed r. But if I change r, the red dot moves, making it red. You can see right there. The rest of what you see here is just formatting. Then the graph on the right comes from this stuff right here. All right. First of all, I'm plotting a horizontal line at e to the r. This is going to plot a horizontal line as a function of n, if you will. And then, this is the hardest part of the code, making those black dots, comes from this ListPlot and table. Table creates lists of things. In this case, it's a list of points. Points of the form n comma 1 plus r over n to the n power. As n goes from 1 to b, where b is the animation parameter, which can get as large as 40 here, and which is equal to 40 right at the moment. All right, table creates a list, and then ListPlot plots those points that are in that list. And again, the rest of this is formatting. All right. To end the video here, I want to add a little bit to this. I want to add another animation parameter. I'm going to call it epsilon. It's a Greek letter. It looks like an E. Here it is. Funny looking E. Call it epsilon. It's going to start at 1 and go down towards 0. What am I going to do with it? How is it going to play in the animation? I'm going to make horizontal lines, not just at y equals e to the r, but also at y equals e to the r plus epsilon and e to the r minus epsilon. So I'm going to create 3 horizontal lines, in fact. Now you see the 3 horizontal lines. Let's make r bigger. And again, the horizontal lines, the middle one is y equals e to the r. The one below is y equals e to the r minus epsilon. The one on top is y equals e to the r plus epsilon. If I make epsilon smaller, those lines get closer together. The fact that the limiting value of 1 plus r over n to the n power equals e to the r, no matter what r is, can be illustrated by the fact that these black dots will eventually get inside that window there if n is sufficiently large, or if b is sufficiently large in this case. Okay? That's always going to be the case, no matter what r is, for a fixed r, and no matter how small epsilon is, you're eventually going to get inside that tube. I'll let you think about that. I'll talk about it a little bit more in the next video before we get back into representations of exponential functions.